I'm not going to prove this one here. So this one, the proof is in dumb and input. So I'm just going to omit this proof.
What's a flat module? When you start this
There were
section,
that's my next. Okay, there you go. That's what's next. Okay, good, great, excellent question. Okay, so flatness and tensor products is what's next. Okay. Great question. Okay, so for R modules, there's another functor, right? There's a third functor, and it's an adjoint. So for every R module M, there's a functor called the tensor product functor. Here, so I'm going to write it like this, Rm. So this goes from the category of R modules to the category of R modules called the tensor product functor. Called the tensor product with M. Okay? So this is a functor. And the most important property of this functor is that it's the adjoint of the Hom functor. Okay, so the most important property, or maybe it's defining property if you want, but we're going to give some other descriptions of it. Important property. Okay, is that for all modules, R modules, V and W, is that we have the following isomorphism. So morphisms from V tensor R over M to W are isomorphic to morphisms from V to MW. Okay, so maybe I can move this a little bit over. Oh no. Do I have a lasso or something? Anyway, it's a little off. It doesn't matter. But moreover, right, the pair, moreover, that there's two functors, right? And we have a pair of adjoint functors. The pair here. Okay, so we have this functor, the tensor product functor, and then we have this functor, which is the functor represented by M, the Hom functor, right, is an adjoint pair of functors. Okay, and so again, the terminology here is that so the two ways we can say this are that this thing here, this is a left adjoint of this thing, or we could say that this thing equivalently is the right adjoint of this thing. Okay, so there's these two things are these two expressions are equivalent, saying that one is the left adjoint and one is the right adjoint. Okay, so we have this adjunction. Okay, so so we get some freebies right away, right? So the freebies we get are, well, so left adjoints preserve colimits. So this is left adjoints preserve colimits, and right adjoints preserve limits. Okay, so so right adjoints preserve limits. Okay, and so what does this tell us? So this tells us that this thing here is a right exact functor. So for free, we already know that it sends surjections to surjections. So a surjection with respect to this functor is a surjection. Okay, and here we have that this thing is left exact. So injections go to injections, but we already knew that because representable functors preserve limits as well. So this was injections. So hom or mod r. All right, and then I'm going to let you guys go. So mod r injections. So this is an injection. Okay, but this part here we already knew. So we already knew this because representable functors preserve limits. Knew this. Representable functors preserve limits. Okay, and this is a representable functor. So right, it's the hom of something. Okay, and so what is so to answer your quick question, a module will be flat when it takes injections to injections, right? So module M will be flat if this functor is exact, right? And we only need to check injections to injections. And so next time I'm going to give you an explicit description of what this tensor product actually does, and like, okay, so like we have this like abstract thing. I said that it's an adjoint, but I didn't tell you how to work with it, and I'll do that next time.
See you, Taylor.
See ya.
Thank you.
You're welcome.